The American pistachio industry covers over 300,000 acres of California's Central Valley, generating billions of dollars and dominating the global market. But look closely at those hundreds of thousands of acres, and you'll find a startling reality. Almost every single tree traces its lineage back to a single seed, the Kerman variety, brought to the United States from Iran by a botanist in the late 1920s. Relying on a single genetic profile across an entire industry is known as an agricultural monoculture. When every plant in your supply chain shares the exact same biology, they all share the exact same vulnerabilities. The entire American pistachio supply is tethered to the biological timeline of that one aging Iranian seed. And as the environment around it changes, that timeline is breaking. To bloom properly, the Kerman variety requires a strict period of winter dormancy. This metric, called chilling hours, means accumulating 900 to 1,100 hours below 7.2 degrees Celsius. But California's winters are warming, missing that 900-hour baseline. Without rest, crop yield collapses. Even if a Kerman tree gets the chill it needs, it faces a second hurdle at the end of its life cycle. Kerman nuts mature very late in the season. That late harvest perfectly aligns with the late summer flight of the navel orangeworm. These pests infiltrate the split shells of mature nuts, causing severe damage and leaving behind harmful aflatoxin contamination. The industry is caught in a trap. If the winters are too warm, the nuts won't grow. If the summers are too long, the pests destroy them. The Kerman needs a biological successor. In the 1990s, University of California researchers Craig Carlson and Dan Parfit saw this crisis coming. Their mission was to build a new, resilient pistachio from the ground up, utilizing precise genetic selection to bypass the Kerman's fatal flaws entirely. This chart illustrates the complex breeding process. It maps offspring from parent lines 235 and ES2, combining to create seedling B1569, producing dozens of unique seedlings. They needed a tree producing large nuts, bearing fruit early, and maturing quickly. Only one hit every target, selection S43. Through systematic elimination, the breeders isolated a specific genetic variation. They engineered a precise biological countermeasure to climate risk. Selection S43 was officially named Gumdrop, a moniker inspired by the unusual, completely harmless gummy deposits that form on the outside of its fruit. This timeline shows how Gumdrop solves the winter threat. Blooming 11 days earlier than Kerman, it requires significantly fewer chilling hours. By summer, Gumdrop's rapid biological clock allows harvest 24 days before Kerman, pulling the crop completely out of the navel orangeworm infestation window. By literally shifting the pistachio's biological timeline backward, Gumdrop successfully dodges both the warming winter and the late summer pest cycle. Agricultural trials running from 2007 to 2015 proved Gumdrop's economic viability. It matched or beat the Kerman in premium kernel size, natural split rates, and overall payable yield for the farmers. But the monoculture model created one final, massive logistical bottleneck. When millions of identical trees ripen at the exact same time, it puts immense strain on the specialized shaking equipment required to harvest them. So the breeders introduced a larger strategy. By utilizing Gumdrop alongside other newer varieties like Golden Hills, growers could create a sequential harvest series. This graphic shows how the series staggers the maturation calendar. Gumdrop is harvested first. Golden Hills follows 10 to 12 days later. Finally, the Kerman finishes the cycle 12 days after that, spreading the equipment load over a full month. This cascading harvest schedule turns a month of industrial chaos into an orderly sequence. Widening the harvest window ensures the American pistachio industry remains viable, even as its original genetic clock begins to fail.